In the last video, we showed that if we have n particles with masses m1, m2 up to mn on the x-axis at positions x1, x2 up to xn, then the center of mass is at x bar equals sigma mi xi divided by sigma mi. In exactly the same way for n particles on the y-axis, we can show that the center of mass is y bar is sigma mi yi divided by sigma mi. If we combine these results, we can think of n particles of masses m1, m2 up to mn at points x1, y1, x2, y2 up to xn, yn. Then the x-coordinate of the center of mass is x bar, which is sigma mi xi over sigma mi, and the y-coordinate of the center of mass is y bar, which is sigma mi yi divided by sigma mi. If we combine these results, then we can see that the center of mass of the n particles is the vector x bar y bar is 1 over sigma mi times the vector sigma mi xi sigma mi yi. Or we could write that in the form that if we have n particles of masses m1 up to mn at position vectors r1, r2 up to rn, the center of mass r bar is equal to x bar y bar, which is sigma mi ri divided by sigma mi, which is the same as 1 over sigma mi times the vector sigma mi xi sigma mi yi. This result is also true for 3 dimensions. A mathematical justification of this result is in the PDF notes which accompany this video. Now let's do an example. Find the center of mass of the 4 particles with masses 2, 3, 5, and 2, as shown in the diagram. Okay, let's look for the solution of this. Oh, mind of its own. We're going to use the idea that our center of mass is equal to sigma mi vector divided by sigma mi. That gives us that on the top line we have a mass of 5 times the vector 0, 0. That's this one here. Then we've got 2 times 3, 0, 3 times 4, 4, and 2 times 0, 6. So that's plus 2 times 3, 0 plus 3 times 4, 4 plus 2 times 0, 6 divided by 5 plus 2 plus 3 plus 2. The top line comes out to be 6 plus 12 is 18. And the bottom line comes out to be 12 plus 12, which is 24, divided by 5 plus 2 is 7, plus 5 is 12. So that is 1.52. Okay, is that a sensible one to have? 1.52 is there. Does that look reasonable? Well, it's towards the bottom of the picture, but the heavier weights are over here. It's towards the left of the center of the picture, then the heavier weights are over here. So yes, I think I would say that 1.5 looks quite sensible. Okay, now let's do another example. The center of mass of the 4 particles shown in the diagram is at 3, 2. Find the value of m. Well, let's see what we can do if we're looking for a solution. We're going to use the formula that the center of mass, R bar, is sigma mi r vector I divided by sigma mi. This gives us that r vector, center of mass, is 3 times 0, 0, that's the first one, plus m times 5, 1, plus 6 times 5, 3, plus 3 times 0, 3. Divided by, adding up the masses, 3 plus m plus 6 plus 3. Well, that gives us the top line of the vector is 5m plus 6 times 5 is 30. The bottom line of the vector is m plus 6 times 3 is 18. 3 times 3 is 9. Add them together, you get 27. Divided by 3 plus m plus 6 plus 3 is 12 plus m. This has to be equal to 3, 2. If we just look at the top line of that, we get that 5m plus 30 divided by 12 plus m equals 3. Move up a bit, give myself a little bit more board. And this gives us that 5m plus 30 is equal to 3 times 12 is 36 plus 3m. That gives us 2m equals 6. Therefore, m equals 3. That was when we were looking at the x-coordinate. Let's just make sure that the y-coordinate is working, that we haven't made a stupid mistake. The y-coordinate, that's the bottom of the vector. If we're up here, the m plus 27 divided by 12 plus m. There we get m plus 27 divided by 12 plus m is equal to 2. That gives us m plus 27 is 24 plus 2m. Subtracting m, subtracting 24, we get 3 equals m. And so both of them give the same. We can confidently say that m is equal to 3. Examples like this and more are in your textbook M2 on pages 34 to 39. The book has a technique of taking moments to find out the position of the center of mass, which is fine for an XY plane, but it becomes difficult to visualize when you're working in 3 dimensions, and so I prefer not to use the moments technique.